What if I told you that the invisible technology powering our entire modern lives is constantly walking a tightrope? I mean, just imagine for a second a world where your favorite apps, Netflix, Google Maps, WhatsApp, and ChatGPT, just suddenly vanish into thin air. Every single time you send a text message or stream a video, something absolutely incredible has to happen behind the scenes just to keep the lights on. Welcome to This Explainer. Today, we're going to uncover the hidden engineering that literally powers the internet. You know that feeling, right? We completely panic when our home Wi-Fi drops for even 5 minutes, or when online banking is suddenly down right when we're trying to pay for dinner. We completely rely on this constant digital pulse. But what most people don't realize is that there is a massive, totally invisible infrastructure working around the clock to prevent a total digital blackout. The real magic happens inside a facility like this. And I know what you might be thinking, but this isn't just some boring, windowless warehouse. A modern data center is actually a high-tech digital city, and just like a real physical city, it needs power, it needs cooling, highways, and emergency services. To keep this digital city alive without, burning it down or completely bankrupting the builders, engineers use a sacred math known as load calculation. It is the ultimate balancing act. To truly understand how this works, here is our roadmap for This Explainer. We'll look at powering the invisible internet, creating the master blueprint, sizing the backup heartbeat, laying down the cables and protection, taming electrical chaos, and finally, calculating the ultimate efficiency score. All right, let's jump right into part 1, powering the invisible internet and creating that master power blueprint. I want you to put yourself in the shoes of a master engineer for a minute. Your very first job is to figure out exactly how much power this massive digital city is going to need. Now, the biggest mistake a rookie engineer can make here is confusing connected kilowatt with demand kilowatt. Connected kilowatt assumes that every single server, light bulb, and cooling fan is running at 100% capacity at the exact same millisecond. But think about your own neighborhood. Does every single house run their microwave, their air conditioner, and their vacuum cleaner at the exact same moment? No way. And that's exactly why engineers use what's called a demand factor to calculate the realistic real-world usage, or the demand kilowatt. If we actually built the data center for connected kilowatt, it would be insanely oversized and just waste millions of dollars. So, to organize all this electrical chaos, we break the data center down into some very specific load categories. You've got your critical IT, which are the servers themselves. You've got mechanical loads, like the massive water chillers used for cooling. Then you have essential facility gear and your basic office loads. But here is the catch. Not everything gets the luxury of expensive backup power. We have to prioritize. So when a disaster strikes, the servers stay alive while the office air conditioning turns off. Which leads us to part 2, sizing the backup heartbeat so we can survive grid outages. This brings up a really vital question. What exactly happens when the city's main utility grid completely fails? Suddenly, the lights go out, but your Netflix stream, it doesn't drop. Why is that? Well, it's all because of the uninterruptible power supply, or UPS. The UPS is the facility's instant electrical backup. Think of it like massive pressurized emergency water tanks sitting on the roof of a building. The very moment the city water pressure fails, those tanks instantly push water right into the pipes, so you don't even notice a drop in flow. Undersizing these battery systems causes catastrophic digital crashes, while oversizing them wastes enormous amounts of money. Precision here is literally everything. But there is a catch. Those UPS batteries, they only last for a few minutes. They're really just there to buy us time. If the UPS is the emergency water tank, the massive diesel generators are the heavy-duty backup pumps that kick in to keep the city running for days. And sizing these generators is intense. Engineers have to account for block loading. Imagine dropping a massive physical weight onto a spinning engine. You have to know exactly how much electrical weight the generator can take all at once without stalling. They even have to calculate fuel autonomy. Keeping an 8-megawatt facility running for just 8 hours requires over 16 cubic meters of diesel fuel. That is a massive amount of fuel to have on standby. Moving on to part 3, cables, pipes, and protection. Let's lay down some digital highways. Now that we have our power sources, we actually need to distribute that power. Think of the complex network of electrical cables as the physical highways of our digital city. If the highway is too narrow, traffic jams happen, and cables literally melt. To prevent this, engineers put every single cable design through a super strict gauntlet of safety checks. They test for ampacity, which just means can it handle continuous electricity without overheating. They test for short circuits, and even the massive surge of power that's needed just to start a giant motor. If a cable fails even one of these checks, no way, it gets rejected. The really crucial point here is voltage drop. Imagine a really long garden hose. The water pressure at the very end of the hose is going to be much weaker than right at the tap. Well, electricity does the exact same thing over long cable runs. And here is a totally surprising fact that catches a lot of junior engineers. If you pack too many power cables tightly together on a tray, they heat each other up. And because of that trapped heat, they actually lose their capacity to carry electricity. It's like trying to run a marathon in a densely packed crowd versus running on a completely open road. Next up is Part 4, Taming the Electrical Chaos by Managing Harmonics. Now we are shifting our focus from the amount of power to the quality of the power. There is a hidden problem caused by the very technology that makes data centers so advanced. It's called harmonics. When modern servers and LED lights draw power, they don't do it smoothly. They take power in sharp, rapid gulps. This creates electrical chaos bouncing back into the system. Imagine a giant swimming pool where 100 people are just randomly splashing and jumping. It creates turbulent, choppy water. That turbulent electricity is what we call harmonics. If the engineer doesn't design proper filters for this choppy water, it secretly overheats transformers and can literally melt the wires right inside the building. Which leads us right to Part 5, the ultimate efficiency score, calculating PUE. Okay, so now that our city is built, powered, and protected, how do we actually grade its performance? We use a metric called Power Usage Effectiveness, or PUE for short. It's simply the total energy the whole facility uses divided by the energy that actually makes it to the computer servers. Think of it as the fuel efficiency, or the miles per gallon of the data center. A perfect score would be 1.0, meaning every single drop of power goes only to the computers. Why does this matter? Because every single kilowatt of wasted energy costs millions of dollars over the 20-year lifespan of a facility. So where does all that extra energy actually go? Surprisingly, a huge portion of the power coming from the grid isn't doing computer processing at all. It's spent just running massive chillers to stop the servers from melting and overcoming the natural electrical resistance in the wires. Getting a PUC score down to 1.3 is considered highly impressive in the industry. That basically means for every 1 watt used by the server, only 0.3 watts are spent on cooling and overhead. Finally, Part 6, the capstone. Let's bring this all together. Picture this, a massive 10-megawatt co-location facility located in Hyderabad, India, operating in sweltering 40 degrees Celsius heat. 10 megawatts. That is enough power to run thousands of homes, entirely dedicated to rows and rows of blinking servers. To pull this off, the design engineers had to use absolutely everything we just talked about. They mapped the realistic demand factor, they sized the UPS water tanks and the diesel backup pumps, they laid perfectly spaced cable highways to prevent heat traps, filtered out those turbulent harmonics, and optimized the cooling to hit a stellar PUE score. It is an absolute modern marvel of engineering that happens completely silently in the background every single time you hit search on your phone. But here is the final thought I want to leave you with today. AI models are growing exponentially, and they are incredibly power hungry. So, as artificial intelligence demands even more massive digital cities, how will the next generation of engineers redefine the limits of power? Thanks so much for joining me on this explainer. I hope you never look at the internet the same way again.